I want to talk a little bit about force vibration because that's a major component that we kind of rush towards the end of the lecture series. So in the following companion video, I'm just going to look at force vibration, no damping. One problem looking at rigid bodies, but again, to play with the definition, and everything really comes down to second law. And I promise I won't do that very much, but it's kind of fun to do it once in a while. So sum of forces equals mx double dot or ma, but framing the equation based on the equations of motion so that I always get some result that makes sense. So if I look at this and I follow along, I have an external force which is applied to the cylinder as shown. What omega A will cause excessively large oscillations of the system. So what's going to be the natural frequency of the system? I have here information. I have K equals 30 newtons per meter. I have a bit of information I'm going to use later, which is that whatever displacement there is in the initial spring is associated with a static equilibrium. I have the displacement, positive x in this direction and positive downwards in the end for the forcing, which is F0 sine omega AT. The mass is given as 5 kilograms. I have a pulley here. I have a pulley here, and the other mass is 2m, so 10 kilos. You'll see that there's a wraparound here, and it goes back down here to connect to the second mass. So I know this will affect the tension here compared to the tension here. So if I look at it, I have kx plus x static. I have the normal force acting upwards. I'm going to treat this as if it's sliding. If I were a little bit more careful, I might put normals for each wheel, but that's not important here. I have 2 mg and 2t acting on the body. I have tension in the cable, which is acting upwards. I have a positive downward, so it corresponds to this direction. And I can sort of save time and not have to write this equation twice. I have force equals F0 sine omega AT. I'm going to get rid of the weight and the static equilibrium term because they're not going to play a role in the vibration. And you should at this point be very familiar with doing this sort of thing with all of your problems. So once you've done that and you have everything sort of worked away, we've just removed the static equilibrium term. We can continue with this. So my two equations are minus kx plus 2t. I should draw the figure. Kx plus 2t equals 2mx double dot. Now, the second mass, which is dropping, is going to go at 2x double dot. So I can have mx to 2 double dot. And what I'll have is this as my system. So positive x in this direction, positive x in this direction. They correspond and sort of lead on each other. I'm going to jump a little bit in the expression by multiplying it by a 2 right away. And that will allow me to get rid of those t's. That ends up with a governing equation, which is going to be mx double dot plus k over 6mx equals 1 over 3m F0 sine omega AT. Now, what you should be noticing here right away is that I've kind of skipped a couple steps. But 2f, 4x double dot m, 2x double dot m, and I've got kx. So if I put all of this together, I will end up with a 6m term, and this will cancel out to 3m. It's one of those things that's worth doing on your own. It's skipping a step, but not a major step. But from that, I know what the natural frequency of the system is, which is going to be square root of k over 6m, and that's the answer that I'd be looking for in this particular problem. So again, everything is going to depend on setting up your equations of motion correctly, getting all of your terms together, and then solving through for everything. Okay, what is the equation of motion for the mass, which is subject to a sudden applied force of 100 newtons that remains constant after application? displacement velocity of the mass are both 0 at time equals 0. So if we start with that, we can say, well, I've got kx in one direction, which is going to be not positive, negative, sorry. I have F naught, which is acting to the right, so it's minus kx plus F naught equals mx double dot, and I end up with x double dot plus k over m equals F naught, so that's the forcing frequency. So I'm going to have a characteristic in a particular solution. The characteristic solution, this is a standard mass spring system. I know it's going to be sine and cosines that I can add. I could do it as a phase delay, but I'm not going to. And my expression for the forcing is going to be F naught K over K. Standard definition. Don't you need the time varying force? No, because it's not time varying. It remains constant after application. Putting in the terms, putting in your zero conditions, so initial position is 0, initial velocity is 0, a equals 0, b equals at minus F naught K, and so you have x equals F naught over K times 1 minus cos omega nt, or substituting all the terms in for your natural frequency, you just get K over M, which is going to be 100 divided by 10 square rooted, and that's your expression right here. Now, the last sort of problem is difficult on its own, but only because it looks difficult. I have here a system which consists of a rod. I have a spring over here and a damper. The horizontal rod, or the uniform rod of mass m, is freely pivoted about the horizontal axis through point O. Assume small oscillations, so very little. You have a distance A here, you have a distance B here. Determine the damping ratio zeta. What are the values of Cc of the damping coefficient C, this thing right here, so the system will be critically damped. So again, all you do in every one of these problems is the same thing. You set it up so you end up with positive rotations and positive moments. I'm going to solve this as a moment question. It's not, that's something you should immediately recognize. And the reason why it's a moment is because it's pivoting about this point. I have the spring force, which is acting in opposition to the displacement. It's going to be pushing down. I have the damper force, which is acting opposite to displacement. I have the distances B and A, which I'm given here. These are the positive directions, and counterclockwise is positive. Sum of moments about O equals I naught theta double dot. Standard minus Ka sine theta, A cos theta, that's the distance. Cb cos theta, theta dot, B cos theta equals 1/3 m b squared theta. Now, that term right here you recognize immediately as a uniform rod pinned at one end. You can do the parallel axis theorem, you'll get the same result. But putting all the terms together, bringing these terms from the left-hand side to the right-hand side, multiplying by 3, so you have nice variables, you end up with 3c over m theta dot, 3a squared k over b squared m theta, and this term is your natural frequency for the system. The critical damping coefficient, C equals m to 2m omega n. You can put all that together. 2m, 3a squared k over b squared m. Substituting in, you get zeta cb over 2a times square root of 3 over km. So putting in the numbers that you have, zeta equals 1 is going to be critical damping. M equals 100, K equals 213 newtons per meter. I put weird numbers occasionally just for getting something out, 1.3 meters and 2.8 meters for A and B respectively. And your critical damping coefficient ends up being 78 Newton second meters. All of this is Newton's second law. And if you don't overcomplicate what's expected of you, it's not so hard to do. If you start to overthink it, it will end up being very difficult. We give definitions, but they're for the governing equations you derive, not necessarily the same value. So for example, one of the common issues with natural frequency is that people will always solve through and say, oh, I've got a spring, I've got a mass, and just put K over M. You have to write out Newton's second law. You write out the equations of motion, you draw it all out, and then you get your answer. And once you do that, you get a good result.